Hi everyone, my name is Piotr and I would like to show you today how to make Async Rust less painful. Let me introduce myself real quick. I've been doing software engineering for almost 18 years now, and I was lucky to participate in a few interesting projects. I did Android at Google, electronic trading at 2 Sigma, distributed database at ScyllaDB, trading APIs at Kraken crypto exchange, and finally replicated SQLite at Turso. Yeah, but why am I even speaking on the Rust conference? So my history with Rust started when one of my teams at ScyllaDB became heavily involved in the Rust client library for our database. Then trading endpoints I was responsible for at Kraken were also written in Async Rust. And finally, at Turso, we not only implemented a replication layer for SQLite in Rust, but also decided to do a full rewrite of SQLite in Rust itself. Having said that, the project called Limbo is surprisingly successful. We've got over 90 contributors so far. The popularity measured in GitHub stars is also pretty solid, like 10,000 stars soon. So if you ever wondered how it is to develop a database, and if you like Rust, come join us. This is an effort to make a community project, so yeah, feel free to check it out. With that off the table, let's get to the core of our presentation. We will be working on an example HTTP server written in Async Rust. Tokyo will be the runtime for futures, and the logic will be really simple. There's going to be a single endpoint which takes a single query parameter post ID, and then when a GET request is sent to that endpoint, it will fetch a post from a JSON placeholder API which returns some sample data, and then it will compute some abstract score for this post and return it in a response. This is what the JSON placeholder returns. It's just a JSON representing a post with an ID, title, body, and user ID of the author. So let's have a look at the implementation. Very basic. We've got a main method which creates a TCP listener, and in a loop it accepts connections and then spawns a Tokyo task to handle that connection. So far so good. The accept request uses Hyper to bring us up from TCP to HTTP, and then rejects anything that's not a GET request with the appropriate path, and then passes the request down to the handle request function. Finally, some logic. Handle request function gets the post ID from the request, fetches the post from the downstream system, computes the score, and then returns it in a response. Very simple, pretty basic stuff. So let's develop it further. Let's add caching to this. So like a score for a post is always the same. So to improve performance, to reduce the strain our server puts on the downstream system, we're going to cache scores that we already computed. Ideally, I would just add a cache in the main, push it down to the accept request, which just pushes it down again to handle request. And then handle request will have some logic, which is for every request, check if it's already in cache. If it's there, return the cached result. Otherwise, do what was done before, just cache the result at the end. That's simple and everything works. It's great. But if we try to compile it, we will get a compilation error. it will say that cache object might live shorter than the future which is passed to the spawn function. Those are the two objects mentioned in the error, the cache variable and the async block in the loop. And this is because Rust has lifetime checker, and Tokyo spawn requires the future to have static lifetime. But we see obviously that cache here is dropped only when the main method finishes, which is when the whole program finishes. But still the Rust checker is not able to figure that out. So let's try to fix this. One way would be to make the cache static. So if the static lifetime is required, let's give them static, right? It's a bit, everything compiles with this approach, although the compiler will warn us that using mutable static reference is not a good, static object is not a good idea. And also we have to use unsafe Rust here and here. So all of this is actually pretty terrible. Let's have another try. Let's do what most people do with Async Rust. So just wrap everything in Arc, right? Because Arc will guarantee the lifetime of the cache. But now we have to clone it, and then like it gives us all this like boilerplate. Plus, performance-wise, this isn't ideal because Arc has like a atomic reference counter, and this doesn't play well with modern multi-core CPUs. So there's an alternative. It's a concept of structured concurrency, and it's more general than Async Rust or Rust at all, but it's very simple at the same time. It basically means like if you've got a function and it spawns some tasks, concurrent, parallel, it doesn't matter. Like before this function returns, make sure everything you spawned finishes. It's a little bit similar to having pure functions with no side effects. It's not exactly the same, but like it's pretty similar. But it makes it much easier to analyze lifetimes. So here's an example how we could implement structured concurrency with futures unordered. Here we don't spawn any Tokyo tasks anymore. Instead, we keep collecting the futures returned by accept request in the futures unordered. And futures unordered allows us to pull multiple futures together. We need select because we want to keep doing two things, accepting new connections and pulling those existing handlers for already accepted connections forward. But with that, we don't need Arc anymore. The lifetime is ensured because all those futures don't need to be static anymore. What do I have here? Okay, yeah. Futures unordered is actually pretty low level, and it might not be the most convenient way of doing structured concurrency. But fortunately, there's plenty of libraries which make it easier. One of them is Moro. And on the right, you can see an example of usage of Moro, which has like something called async scope. And within that scope, anything you spawn there can reference stuff which is declared before the scope, because the scope ensures the lifetime of those futures, right? So it doesn't require static lifetime anymore. This is how it looks, not as a div, but as a final implementation. So you can see that the Moro implementation is actually pretty simple, yet it lifts the requirement for static lifetime. But there's another problem with Async Rust, which you might have encountered. It's basically that futures have to be sent. And this is not something which is like caused by Async Rust itself. Like nothing in Async Rust as a concept forces us to make our futures sent. It's basically Tokyo's fault, which is Tokyo, as probably almost everyone of you knows, is the most popular runtime for futures. And it's amazing, but its maintainers made a decision that it will use by default multi-threaded work stealing scheduler. And with that, it means that your tasks can be migrated between threads. And to be able to do that, they have to be sent by the definition of send. Here you can see few snippets from Tokyo documentation actually describing this situation. And that work stealing is a thing. So it doesn't have to be like that. This isn't the only option. One option is to use a single-threaded runtime, because if there's one thread, tasks cannot be migrated between threads, so they don't have to be sent anymore. And Tokyo makes it possible by using the single-threaded scheduler. An alternative, which is more suitable for multi-CPU servers, are runtimes which don't do thread work stealing. An example of such is Datadog's Clomio, which uses something called shared nothing architecture or thread per core architecture, which in a nutshell is an idea that like every CPU gets its own thread, and whatever is executed there stays there, and the threads communicate between each other, but futures are not migrated. And that allows us to use futures which are not sent. And it also can be more performant because migrating, like making stuff sent, basically means it has to employ some synchronization mechanisms, and those mechanisms usually like clear caches of CPUs. So like if you need all of your performance, then usually it's better to keep stuff happening on a single core and then some other stuff happening on some other core, and don't shuffle it around. Finally, let's have an example of which I borrowed from a blog from Evan Schwartz. It's an excellent blog. I will show you a link to it later. But here's an example of a traditional implementation of some server which accepts requests, and then it calls a DB, calls some downstream systems like ABC, and then it computes some response, right? So traditionally, everything would be wrapped in arcs, like what's stored in context structure here. And we have all those clones, which are all over the place, right? Like if we use Moro for that, we can drop all arcs and all the clones, and code becomes, well, in my opinion, at least more readable, and I believe also more performant. So here you can see them side by side and decide for yourself if you like the traditional way more or the structured concurrency Moro approach, which at least it's shorter, but it has some more advantages as well. And there's the link I mentioned to the blog post. It goes into some more details about performance characteristics of work stealing and non-work stealing runtimes. So to conclude, some of the pains we feel with Async Rust are not caused by Async Rust itself. They are caused by some decisions that were made at the runtime implementation details. And it doesn't have to be like that. We can use structured concurrency to avoid using arcs everywhere. Moro is like futures unordered is probably an overkill. It's too low level, but Moro is totally fine. It actually makes your code easier. Also for structured concurrency, it not only makes it easier for you to think about lifetimes for you and for the Rust compiler, but also it makes many things simpler. For example, if you want to have a graceful shutdown in an async code, that's usually a challenge, because you need to make sure that all the tasks you spawned finish in some reasonable shape. As a structured concurrency gives you that for free, because like everything wraps up in a systematic way. Finally, work stealing runtimes are not the only option. There are other options like single-threaded runtimes or runtimes that don't do work stealing. And with that, you can get more performance, and you can make your life easier by not being forced to make your futures send. Yeah, with that, I think we've got plenty of time for questions, but you can always find me on X or LinkedIn. And remember to check out Limbo if you find it interesting and want to hack around it. We always welcome contributors.